So these are some papers. Thank you. Okay. So so now let's see some simulation result related to this Q learning. Okay. So I will show three programs. In the first program, I will show you the Q learning, how we do Q learning in that toy example, grid world. Okay. In the second program, I will show you how to do conventional Q learning in the edge caching. In the third program, I will show you how to do function approximation in edge caching. Okay. So we are taking, so is this visible or should I make it bigger? Little bit bigger? This okay? Okay. So n grid is 5, it means we are taking 5 cross 5 grid. Okay. We are taking 4 actions in the grid world. So this is the grid world. So we can take only 4 actions, left, right, up and down, okay, or we can say north, east, west, south, 4 action. So I have denoted 4 actions here, like this, okay. Then I have enemies, number of actions. So I have included a size here, it will be 4. So these are the actions defined. Now I have defined the states. So in the states, I have defined this state ID, okay. So what does it do? So in the grid world, so we can have like 2-dimensional coefficient. For example, first is 1, 1, then 1, 2, 1, 3, and either we can also name it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, up to like 25, okay. So these two numbering, so we will have to interchange when we make the program. So I have made this one function that is called state ID, which will give me the corresponding number for that coordinate, okay. So let me run this. Live editor, run. Okay. So state ID is like this. Let's say if I write state ID, oh, it's written here already. So if I write state ID 2, 3, so 2, 3 is what? So 2, 3. So 2, 3 is 12. So we are counting row wise first, okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay. So it gives me 12 here, okay. So NS is the number of total states. Total states are 25, and this is just an example to show you how the numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to like 25, okay. Now I have to define the boundary, I have to define the blockage, and I have to define the jump. So how do I define the boundary here? So here I have taken some state, whatever the state is, if state is less than 1. So for example, I am at this 2, 1, okay, and I take action here on the left side, it will give me 0, okay, but 0 is not in the system, okay. So I have written here, if S is less than 1, it will become 0, otherwise it will be plus 1, okay. Similarly, I have defined here S greater than N grid. It means whenever I go out of the grid, for example, I am here at 2, 5 and I take action right, so it will go to 2, 6, okay. So instead of adding 1 there, it will do -1, okay. So it will only up to 2.5, it will not go beyond that, okay. So that's how That's how I have defined the boundary here. You can also define in another way also. Okay, this is how I have defined. You can write if else function also. Okay, you can write another file also, function file also. Okay, blockage. So we have so we have blockages as 4, 3, 3, 3, 3, 4, 3, 5. Okay, so I have defined these blockages in this here. Okay, and I have written here state ID. State ID will give me the corresponding number. Okay, is this okay? Right? If you have any problem in any of the statement, kindly ask. Okay, then jump. Jump is defined at the 2, 4. So this is 2, 2, 4. This is the jump here. Okay, and blockages. So here I have some matrix SS. So in SS matrix I have put these entries here. So at this point we have the jump, we will get +5, and at this terminal state. So I have just denoted here, just for to see. Okay. Now the reward. So we are just defining the terminology. Okay. So reward we have to define for blockage. It is -1. So we have this grid, and for the jump we have the reward +5, and we have the reward 10 when we reach the state. So you can see here also. So this is the +10 reward when we reach the terminal state. We have jump, then we have +5 reward, otherwise we have -1 reward here. Okay. So here I have defined some parameters for Q-learning. Number of episodes are 1000. So I will visit this grid problem until I reach the terminal state 1000 times. Maximum iteration is 10 to the power 3. We can also reduce it, no problem. So gamma is the discount factor, how I weight my previous results, that is the discount factor. Alpha is the learning rate. Okay, how am I updating the Q values? Okay, how I am learning the Q values. If I set alpha equals to high, it means I am changing my Q value abruptly. If I choose alpha equals to low, it means I am changing the value slowly, Q values. Okay. So here I initialize the Q matrix and I initialize the reward. So here in R I will store all the rewards for all possible iteration and all possible episodes. Okay. So this is kind of a reward log. So now I start the episodes here. I am starting from a random states here. Okay. So these are the 2 dimension. So let me run this. So you can see. Okay. So we are here. So this S is 3, 4. So we are starting from 3, 4. So it will give me the corresponding number from 1 to 25 between 1. So this is the 18th number, 18th state. Now I go next. So this is the epsilon greedy action. Okay. So this is the epsilon greedy action. So with probability 0.1, I will take the epsilon this random action, and rest of the probability with I will take the greedy action here. Okay. So this thing you might be wondering what I have written here. So this thing I have written, as the number of episode will increase, this probability will decrease. It means I will choose less and less random action as I explore more and more. Okay, in the later episode, I won't choose random action. Okay, it's like that. So next I have to seek for the boundary condition if it goes outside the boundary or not. Okay. So the next state will be within the boundary, and I have chosen the number for the next state in the variable is1, and the reward is -1. Okay. And I have to check for the blockage if it is in blockage or not. If I have the blockage, I will put the reward 0. Okay. So if goes in the blockage, reward is 0. Now let's check for the jump. If my present state is the jump state and I am taking the down action, okay. So here, if I am taking the down action, I will go down here directly, okay. So if I take the left action or up action or right action, I will not go anywhere, okay. I will go only like one block apart, okay. But here I will go 2 block apart, so I have to write that here. So I have written that here, if I take the third action, that is the down, I will reach state 4,4, and the corresponding number is this for the state, and my reward will be +5, okay. So this is for the terminal state. If I reach the terminal state, that is the 25, I will get the reward +10, okay. So here I am printing the status here, okay, and here I am updating the Q values. So this is the instantaneous reward, and this is the updation equation. So this is the previous Q, and this is the alpha is the learning rate of the Q, and this is the Q value, that is here, R plus gamma and IS1. So this denotes what? If my next state is not the terminal state, then I will do this updation, okay. Then this iteration is over. I will deliver this variable for the next iteration. So S1 becomes S1 and IS1 becomes IS, okay. And if my next state is the terminal state, that is the 25, I will break the loop and go to the next episode, okay. So where we are, let's run this little by little. So I have here, so 3,4, that is the 18th number. So I am taking the action 2. So I am reaching 3,4 with 0 reward, okay. Why? Because 3,4 is this blockage, okay, and I am taking the blockage action towards the another block. So I am getting the reward 0 here, okay. So let's go to the next iteration. So 3,4. So here you see here, from 3,4 I take one action, that is the above action. I will go to 2,4. From 2,4 I took action here 1. So I will go 1,4 above. I will get reward -1. Okay. So this is how I am printing this. Let me run the whole. So I will clean this. Now let's run. Continue. So it will give me whole. Okay. So after all the episode, it will have learned. So we can check the value function for according to Q value. So according to Q value, now we have to find the policy, that pi variable that we have seen earlier, right? So that pi value. So what we have done here, so we have to find. So this temp will give what is the action corresponding to that state. So we have 25 states, and corresponding action is either 1, 2, 3, or 4. Okay. So it will give me 25 cross 1 vector and corresponding action. Okay. And this is the corresponding value. So we don't care about this value that much. We only care about which action to take so that we can reach the final state. Okay. So this action I can represent this vector in terms of a matrix also. So here what I have done, I just converted into a matrix form. Okay. So I represent it in terms of this policy POL. Okay. So this POL is denoted by like this here. So if you are here at the first state, you take the second action, that is go right, and if you are here, let's say here we have jump right on 3, so you take 3, third is down, so you will reach here. Here you also 3 means go here, 2 means right, you go here, you will reach the terminal state. Okay. So if I represent in terms of these symbols, I have denoted like this here. So you see, you choose any of the state, and you will reach the terminal state very fast. Okay. So for example, I choose, let's say this one. So here it says go above, I go here. It says go right, I go here. then again it shows go right. I will go here, then we have jump here, I will go here directly, then it shows go down, I will go here, and it shows go here. I have reached the terminal state. Okay, you will start from any state and it will reach the terminal state. Okay, so this is the policy we have learned. Okay, and here we have plotted the values here. Okay, so this is just a pictorial representation of these values. Okay, any question here? Okay, this is simple, right? Okay, so now let's see the program on edge caching. So here, we have chosen 100 files, total 100 files for simple example, at 20 is the size of cache. Okay, and number of states to be 8 for simplicity, and the states we are defining as using the GIF distribution. So popularity profile is a vector. Okay, so that vector we are defining using the GIF distribution. Okay, GIF distribution is nothing, just like a probability distribution. Okay, you have uniform distribution, Poisson distribution, okay, binomial distribution. Similarly, you have GIF distribution for probabilities. Okay, so it will give you a vector given it has 2 parameters. So this first parameter is the GIF parameter. So I have provided some values here. So it will give me multiple vectors. Okay. So these states are thus probability vectors here. Okay. So you can see here, so these are 100 cross 8 probability vectors. It means I have 8 states and each states contain a probability vector of 100 cross 1 and each vector sum up to 1 because it is probability vector. So similarly, I have taken action to be 8 also, and this is a sum1 function. Sum1, it sum all the values to 1. Action also I have generated using GIF distribution, but action should be sum up to L. Okay, we have seen yesterday action should be sum up to L, the q values, small q. So I have multiplied here L. So these actions, so this is the vector of actions, it will be sum up to L. So L is here 20. Okay, we can check also. So I have written here some actions and it has come out to be 20. So these A, B, C are the parameter to define the reward. Okay, so I have chosen some values here and I have defined the reward like this. Okay, in terms of P and Q. So we are doing the conventional Q learning. So here we define the parameter similar to the previous grid world problem, and these are the Q matrix and the reward matrix to store the reward. So starting state is a 1 state. You can also choose the random state, no problem. And this is the epsilon greedy again. Okay. Then the reward. After you have chosen the action, you will get 2 things. One is the next state and the reward. So the reward I have defined using this function P and Q here. Okay, so I have to supply here the next state P and my action Q. It will give me the reward. Okay, so according to my states and my actions that I have gotten here, IA1 I supplied here, I will get the reward. Okay, from current state I took this action IA1, I will get this reward. Okay, and next state I have chosen random here. Okay. So here I update the Q values similar to the previous. I write the same equation here and update the Q values and I proceed for the next iteration. So I change the variable is equals to is1, it will go to the next iteration. Okay, and this will go on. And after that I save in this Q2 file this reward gamma is the discount factor, alpha is the learning rate. Okay. So this is where my Q learning will learn about the caching. Okay. In what state, what action to learn, what action to do. Okay. Then I choose the maximum, I maximize the Q because I have to maximize the reward. Okay. Q is made of the reward, made up of the reward. So that way I will get the policy here, and I can plot the this cumulative rewards. So here I plot the progress of this R here. So you see here I am learning the these rewards. So earlier rewards are very, very low, and as soon as the value in the Q matrix are getting filled, I am starting to getting better rewards. Okay, that's the idea here. Okay, any question here? What is episode, what is iteration? Okay, last time I gave you one example for the like building. Okay, so you are trying to explore some building. Okay, so I gave you an example that you want to go to Kalpana Madam office, so that is your goal. So you started today and you searched around, this is the new building for you, and you searched around and somehow you went to the Kalpana Madam office or not reached. So this is your one round. Next day you arrive again and you try to explore again, because this is a big building, and you somehow reached by taking some epsilon greedy action here and there. So this is your second round. Next day you come again, you will now not search that much, and you will reach your destination. Okay, so this is a round, and iteration or steps are the one. So whenever you enter the building, you will see some gates. You will take action, either go left, either go right, or you take straight. Or if you are deep in the building, there will be 4 actions. Either you go left, right, up, down, behind also, back also. Okay. So they are all possible action. So these will action also be one by one. So these are steps that you will take to reach your destination, your goal. Okay. So this will be one round until you reach the terminal state, or you have exhausted the maximum number of iteration. Okay. Until you are exhausted, you don't want to find out. Okay. Because things are limited. Okay. So I have chosen here. So here there is no terminal state, there is only maximum number of iteration. Okay. Earlier in the grid world, there was terminal state. So as soon as I reach terminal state, I will not go to the maximum number of iteration. I will stop there. Okay. Any more question? Okay. So let's move to the third program, that is based on the Q function approximation. Okay. Okay. So most of the rest of the things are similar. F equals to 100, L equals to 20, number of states are 8, and states are defined as if distribution, number of actions are 8, and they are all sum up to L, and sum of L is this 20, sum of action is 20, that is shown here. ABC parameters are same, and this reward is defined like this, and we have this CC. So CC is what? The coefficients of function approximation. So earlier we defined 4 coefficients, right? So in those coefficients we define the variable u. Okay. So this is that. So it has 4 values here, 1, 2, 3. So it has only so here I choose only 3 values because 1 was constant there. So theta 1 was constant, so I choose only 3 values here. So it depends on state and action. Okay. So these are the coefficients. Okay. So these are the same parameter. So instead of alpha, I am choosing beta here. So this is to update the theta. So this is also the learning parameter. Okay. But instead of updating the q value, I am updating the theta. So here I have chosen q, r, and theta, 3 values. Okay, to initialize it. Okay, I start from the random state in each episode. Then I do the epsilon greedy action, okay, based on my Q values. Then I get the next state and reward. Next state is based on this IS and present state and my action. And I get the random state is the next state, okay. So this is the Q value, okay. So this is the part of the update equation, okay. And I calculate this, so this is just the update equation, theta equals to theta plus the learning and this error that I represented there in terms of delta there in the equation, okay. If we can see here, I represent it in terms of this delta, this u into delta, and this thing is beta here, and this is delta, okay. So this thing I have written here, these are the coefficient and these are the even delta here, okay. And with this I will get the Q function approximation, that is C1 into TH, okay, this thing, this approximation, okay. So this way I will get all the Q values here, okay. So here I am updating from the CC function, I will get this value C1, okay. Then I will calculate the temporal difference, that is the delta here, this delta, and I will update the Q using this equation. Then I update the Q value using this equation, okay. I have written whatever is there, as simple as that, nothing is here and there, okay. This is for the next iteration, and I have just, this is the loop, rest of the loop, okay. So in the previous program I saved the result. Why I saved the result? Because I can plot again here just to compare. So I can see here, as soon as here you see here theta is learned very quickly, let's say in 4 or 5 iterations, and it start to giving the better rewards, and it goes on continuously, okay. While Q learning takes very long, so it takes like approximately this is 10, 20, 30, approximately 30 iterations to reach that much, and here I am reaching approximately in 3 or 4 iterations, okay. So normal Q learning, it takes very long to reach that much, it takes longer to learn, okay. Okay, any question here? So this is very simple. Grid world problem compared to it is also very difficult. If you start to make this program from scratch, this grid world problem is more difficult than edge caching problem, okay. But it is good to understand this grid world problem before going to the complex program like edge caching or function approximation. Any other question in this program or related to Q learning or edge caching or any other thing? Yes. Yes. There are also algorithms that implement caching at the devices also. So for example, if you open the YouTube, it has like turn on the recommended downloads. So that is like device caching. In Netflix also there, and Prime Video is also there, okay. So these are like device caching also there, okay. So we have only covered only a small portion of the edge caching. There are also different types of caching also there. Device to device caching and base station caching, combined caching also there, terrestrial based caching also, non-terrestrial based caching also there, okay. No other question? Everything okay? Okay. Okay, then we can conclude it. So afternoon, we will see some MATLAB codes on MIMO. Okay. So these codes will be shared to you. These are in this laptop. Kalpana ma'am will share it to you. Okay. You can look at them later. Okay. Okay. Thank you very much. So now we will be doing this MIMO and massive MIMO based exercises. Okay. So this document. So this is an exercise document. This is based on this book, Fundamental of Wireless Communication. Okay. So this document has 3 sections of exercises, MATLAB exercises. One is single user MIMO. Second is multi-user MIMO. Then we have hybrid beamforming for multi-user scenario. Okay. So we will go one by one, and we will see in MATLAB. Okay. So has this been shared to you or not? Okay. Kalpana ma'am, can I share this with you and you can share with all participants?
Yes, sir, I will share. Whatever you are giving it to me, yeah, I'm giving it, I'm sharing them.
Why don't you sit now down?
Now,
WhatsApp group, should I give it, sir?
huh?
Mail IDs you want or WhatsApp group, sir?
I will share with your email. You can share with your.
Okay, sir.
Your email is.
Kalpana, sir, KALPANA
Yeah.
at the rate of nitw.ac.in.
Okay. Okay. So let's read it. Single user MIMO, first section. Let M and N be denote the number of antennas at a transmitter and receiver respectively. In addition, let P and Pi denote the total amount of transmit power. So P denotes the total amount of transmit power and Pi denote the power allocated to the ith stream. The noise is assumed to be AWGN, additive white Gaussian noise, and its variance is assumed to be normalized to 1. We also assume that the eigenvalues are sorted according to their magnitude, that is in the decreasing order. Okay. So exercise 1, let M equal to N equal to 4 generate IID Rayleigh-Fittig channel matrix H of size n cross M, which is a complex number, and where its elements are distributed at Cn01, circularly symmetric complex Gaussian. Look at the eigenvalues of HH Hermitian for few channel realizations and change the value of M and N and see the behavior of eigenvalues. Okay. So So here this is the exercise 1, and everybody can see here, right? So I generated the H matrix of size n cross m with Cn 0 1 random variables, and I took the eigenvalues of H Hermitian as said. So this is the result I see here. We can change the value here. So let's say I choose here 8 and run again. So what did we see here? The value here are increasing little bit. Okay, these eigenvalues also. Okay, and eigenvalues are real because this is a Hermitian matrix and are positive also. Okay, and they are in the sorted order. Okay, second exercise. So this is the first exercise is easy, right? The second is plot the CDF of the eigenvalues of H Hermitian over 1000 channel realizations. Okay, when m equal to n equal to 4, m equals to 4, n equals to 16, m equals to 4, n equals to 28. Three cases. And summarize the main behaviors of the eigenvalues with regards to dimension of H. Okay, be careful with using the EIG function in MATLAB and the order of eigenvalues. Repeat the exercises when the eigenvalues are normalized by 1 by n. Okay. Here, so I have created one file, that is EIG CDF. Okay, in that I am inputting the variable H, and which is giving me this curve for the CDF. Okay, let's see what is in there. So this is a simple M file where what I am doing here, I have the size of H, I am taking size of H. So H is what? I am generating 1000 channel realization. So N sim is 1000 and N cross M matrix. So I am generating 1000 channel realization. So this is a 3-dimension matrix. So third dimension is 1000. Okay. So that way I will have 1000 matrix in one go. Otherwise, what can I do? I can do the for loop and generate the matrix again and again. Okay. It will take more time. So I have generated all matrices, 1000 matrices in one variable. Okay. Here I am taking the size, and E, in E I am storing the eigenvalues. Okay. So min m comma n means the eigenvalues. Number of eigenvalues of a matrix is equal to min of m n comma n. Okay. So here I have taken the eigenvalue of H Hermitian. Each matrix I am taking the one by one matrix, and I am taking H Hermitian, then I am taking the eigenvalue, and after that what I am doing, I am sorting it in descending order, and also I am normalizing by 1 by m n. Okay. And I am storing in this E naught. Okay. Then this E naught, the minimum of, so it may also contain some 0 value if the matrix is large. Let us say 4 cross 5 matrix I have. Okay, it may contain other entries also. So I am choosing min m comma n values 1 to min m comma n, and I am storing it in E variable. So in one row, E has how many rows? 1000 rows, because n sim is 1000. So E has 1000 rows. Okay, so in each row I am storing eigenvalues. Okay, in the sorted order. So first will come the highest eigenvalue, second will come the lowest eigenvalue, and so on in sorted order. Okay. Now what I am doing here, I am plotting the CDF for each eigenvalue. Okay. So I am running this loop here, and I am taking each column one by one, and I am sorting it, and I am plotting this CDF. Okay, is this part okay? So I have taken one column. In one column, so this temp variable will have 1000 values in sorted order. And this sorted order, what I am doing, when I am plotting, I am assigning them value from 0 to 1. Okay, that way I will get the CDF. So you see, I will get. So I was using m equals to 4, n equals to 4. So I will get 4 lines here. Okay, because this is a for loop here. Okay, so it will generate 4 lines here in the plot. Okay, is this part okay? Now similarly, what I have done, I choose n equals to 16, and I have plotted it here. So here m equals to 4 here, n equals to 16. So total eigenvalue are minimum m comma n, that is 4. So I have 4 lines here. So here you see the values are little bit different here. Okay, if we choose n to be different, and if I choose n to be very large, these value are little bit lower side. Okay, so this here I took n equals to 128, generate the realization, and took the put it into the EIG CDF function, and it will generate all the CDF values. Okay, so this is the part here. Okay, so for all 3 cases I have generated these values. Okay, so behavior of the eigenvalues you can also see here. So earlier it was some high value, and it getting little bit lower. Any question up to this point? Okay, any question in this code, how to generate the code, or any explanation? Everybody know MATLAB, right? So exercise 3, for a point-to-point system, the optimal precoding and combining matrices can be achieved using SVD. SVD, professor has explained in his slide, right? SVD based precoding, but it requires channel sheet information at both transmitter and the receiver. Okay, so precoding can be achieved by using SVD based transmission. So in this exercise, you will investigate the impact of power allocation. Over 1000 realization, let m equals to n equals to 4 and p is in -5 to 5 dB. Plot the ergodic spectral efficiency of MIMO system when these 4 cases. First case is you allocate power to the first stream. Second case, you allocate power only to the fourth stream. Third case, you allocate equal power to all of the stream. And the fourth case, allocate power according to the water filling. Okay. So let's see. Okay, did you understand the question, right? Okay. So I choose m equals to 4, n equals to 4, same, and I have made some function sec1, section 1 E3. So let me see where it is. It's here. So here what I am doing, I am providing the value m and n, and I am generating the channel here correspondingly. I have taken the eigenvector here. Do you know the capacity of the SVD channel? What is the expression for that? Everybody know or no? Don't know? Do you know? Okay. So let me write it here. So you have y equals to h x plus n, or let's say w. Okay. So this is your, let's say, 4 cross 4. Okay. This is 4 cross 1, and this is also 4 cross 1, and this is also 4 cross 1. Okay. Now I take the SVD. So h is equal to u, let's say sigma, and V Hermitian. Okay, this is the SVD. So if I multiply here U Hermitian Y, what will I get? U Hermitian, then I will have U sigma V. So this is for H, then X. So then I have X, then U Hermitian W. Okay, so U Hermitian U is identity matrix. Okay, so here you can note that U Hermitian U is identity and V Hermitian V is also identity. Okay, so what I am saying here, let's say I am writing this as Y bar, so I can write it as sigma into X bar plus let's say W bar. Okay, and let's say sigma bar is equal to let's say sigma 1, sigma 2 and so on. Okay. And W is let's say Cn 0 comma n naught. Okay. So I can write the capacity C equals to log 2 1 plus so let's say expectation of X bar Hermitian I is equals to Pi. So Pi sigma I square divided by n naught and summation over all I equals to 1 to the number of streams. So here we have 4, so it will have 4. Okay. This part is okay. So every transmitter has some power constraint. Okay. So this transmitter also has some power constraint. So each stream here xi, so x is a vector of 4 cross 1. So each stream has power pi. So total all streams have power p. So I equals to 1 to 4, power is pi. Okay. So pi is this thing. Okay. So if I write this problem, let's say maximize this capacity subject to pi for all I equals to 1 to 4 and subject to this power constraint summation I equals to 1 to 4 pi equal p. So this problem is called water filling problem, right? So here this sigma I square is coming. Okay. So instead of calculating the SVD, we can calculate the eigenvalue decomposition of HH Hermitian. Okay. It will be equivalent. Okay. So if I am calculating H Hermitian H, so I will get some diagonal matrix D here and I take the diagonal values in a lambda vector. So lambda I will have vector of 4 cross 1. Okay. Let me run it so we can see this. Okay. So let's put some marker here and go here and run this. Okay, it has come here. So you see we have 4 values here. Okay, and D is a diagonal matrix here. Okay. So now I have to take minus 5 to 5 dB transmit power here as said in the question. So minus 5 to 5 dB. So I have chosen 10 values here. So n dB will be 10. Sigma square is 1. So this n naught I have taken 1 here. Okay. And this rate function I have denoted this summation as a function here. So I am writing here real sum this summation log 2 1 plus p here into lambda. So lambda is the sigma I square divided by sig 2 is this n naught. Okay, the same thing. Now for each dB, so for each dB, each power of transmit power value. Okay, let's run it. So this is the total transmit power. So let's say I choose IDV equals to 1, so it will give me minus 5 dV transmit power, which is equivalent to this value, okay, 0.316. Okay. So case 1 says I will allocate all the power in the first stream here, P1 equals to P and rest of them are 0. Okay. So case 1 I did this and calculated the rate. So rate fun is the function that I defined here. I put P here, it will give me the rate, corresponding rate. Okay. And I am collecting all the rates in this variable R1 comma IDV. Okay. Everybody is getting this right? Case 2 says put P4 equals to P and rest of them as 0. So P4 is equals to PT and rest of them are 0. I am calculating the rate again. Okay. The third case is choose all power to be equal, P by 4. So I choose all to be 1 by 4 into PT and I calculate the rate here. The case 4 is water filling algorithm. Okay. So I have implemented water filling algorithm using CVX. Okay. So this function I have made using CVX. So everybody know about the CVX? If you know the how to implement the solution, how to know the solution of water filling, you can use that. Or if you don't know, you can use directly CVX. Okay. So this is the solution for the water filling function. I am giving the value here lambda, the transmit power constraint, and the sig2, that is the n naught here. Okay. First I write here CVX begin. Quiet means it will not produce any unnecessary output in the command window. Then I define the variable that I want to maximize. So here I have Pi here. So I define here Pi and its length is n, and these variables are non-negative because these are power variables. Power cannot be negative. Okay. Then I define the SNR. SNR is what? P into this sigma I square divided by n naught. So that's what I written here, and then sum log 1 plus SNR. Simple. And I want to maximize it, so I write here maximize. Subject to the same thing, subject to sum of PT less than equals to PT. Okay. I can also write equal to also. I have to write double equal to ensure this is a equality constraint here. Okay. There is no problem because this is a linear constraint. Okay. Okay. So I write the same equation here. Any problem here? CVX is very simple. You can write it. If you don't know how to write the solution for the water filling, you can just write the CVX code and you will get the solution. Okay. So here, so we are here. So let's run this. We will get some rates. So it's saying busy here. So the CVX code is solving it. So it is showing error, undefined function of CVX begin. It means this system doesn't have CVX. Okay. Huh? What is CVX? CVX is a solver that is available online freely for the academic purposes, and we can use this to solve. Yeah, it can be integrated with MATLAB. Can I download it and show it? Okay. So if you go here, so CVX is used for convex optimization. Yes. Windows 64. So CVX is very easy to write the program. Okay, if you write, actually MATLAB also has some built-in solvers, but it's difficult to write in that. You have to define in a different way. So for example, fmincon you have, okay, and lin program you have for linear programming. Okay, so this is CVX downloads. So let's go to home and open home, set path, add with subfolders, then this file, this folder, save. Close. Okay. Next, let's go to command window and write cvx downloads cvx64, cvx here, then cvx setup. If you write cvx setup, it will install the cvx. Okay. So process is very simple. You just add to the set path and run this cvx setup. It will set up all the solver automatically. Okay. So two solvers initialize, HDP T03 and Sidumi. And these are the commercial solvers which requires license. Okay. If you request them using your email ID, institute email ID, they can give you academic license. Okay. But you have to provide your email for that, only for academic purpose. Yeah. But for commercial, then you need to pay. So let's now run this again. Section this. Okay, let's run this. So this is running. So we have some error. So 4 cross 1, 1 and 1. Let's go inside. So this SNR is affine expression subject to so I don't know why it is not running. It was running on my computer. Maybe CVX version I was running, maybe the older one. Okay. So, what can we do? So what can we do? Huh? Yeah. In my laptop it was running fine.
Some problem is this, sir.
Yeah, this CVX is not running here, but it was running in my laptop.
That's fine.
Yeah,
Okay.
maybe some problem with the version.
Yeah, maybe yes. Okay, so we will go to the next question. Okay. I will share you the PDF file after running this. You can here we can publish it, right, with the result. This is a publishing option, right? So I will, with the results, I will run it and send it to ma'am, so she can send it to you. Okay, the run file. Okay, with these. There is no change. Everything is okay. Okay, and let's go to the next question. So here in the water filling, what will we see that we will, let me tell you. So we will see the result like this. So water filling will have the highest rate if we increase the SNR, and equal power allocation is like this. So at high SNR, equal power allocation, and this is water filling. Both will merge into one. So at high SNR, equal power allocation is optimal. That's what is the conclusion here. Okay. So we can repeat this exercise for E4. We can repeat this exercise for different number of n values and see different observation. Okay. Now this E5, okay, this point is clear. So point here is equal power allocation is optimal at high SNR. Okay, so no need to go for complex algorithm at high SNR. It will approximately, you will get the, with water filling, the same values. So let's come to E5. In E5 we are talking about the correlation. If channel has some correlation, what will happen? Okay. So one simple way of modeling channel correlation at the transmitter is using a exponentially correlated MIMO channel model. So in this model, the correlation effects are observed at the transmitter according to this. So here we generate the channel H using these two matrices. So HW is a CN01 matrix, complex Gaussian matrix with unit zero mean and unit variance. Okay, and R is a matrix, so that is given below, and we multiply that R matrix. So R is a correlation matrix. So the H matrix will have some correlation. Okay. So this R is the matrix given by like this. This type of matrix structure. So here you see we have one row n minus 1, then it's like row 1 to row n minus 2, and so on. This type of matrix structure is called the topless matrix structure. Okay, there is a MATLAB inbuilt command called top, TOEP, and you can generate the topless matrix using that. Okay, after you generate the topless matrix, you can multiply with CN01 generated matrix to get the correlated channel. Okay, so after you have generated the correlated channel, we can apply this water filling algorithm, equal power allocation, to see what happens to the rates. Okay. So in the slides also by professor, you have seen that correlation reduces the rates. Why correlation reduces the rates? Because sir has said about the condition number. Okay. Condition number and the rank, those are most important thing for a channel. If the rank of a channel is less, we cannot transmit more than the rank. Number of data stream cannot be more than the rank. So let's say here we have 4 cross 4 matrix here. Okay. So let's say its 2 columns are the same. 2 columns are the same. So its rank will be 3. If 2 columns are the same, it means there are only 3 independent columns. If 3 independent columns are there, it means rank is 3. If 3 rank is there, we cannot transmit 4 streams from here. We can only transmit 3 streams. Okay? Even if we try to transmit 4 streams, the 4th stream will be lost or it will cause interference to others. Okay? So what we are trying to say here, correlation reduces the rates. And condition number, if it is not close to 1, it will also reduce the rates. Okay? So here the value of the row here in the R matrix, what does it tells? It will increase the correlation. If we increase the value of row from 0 to 1, it will increase the correlation here. Okay? So here, let's say row here. So it shows that the 1, 2. It means the entries between first transmit antenna and second transmit antenna is correlated by this value. Okay? So if we have correlated entry, it will increase, it will decrease the rates because it decreases, it worsens the condition number. Condition number is not close to 1. Condition number will become high. Okay? Okay, this part is clear. Now, what is the meaning of square root of a matrix? So here you have to multiply by the square root of this matrix. So how will you calculate a square root of this matrix? Okay? Are you aware of how to calculate the square root of matrix? Okay. Let me tell you shortly in brief. So let's say we have matrix R. If you want to take a square root, in MATLAB you can just write SQRTM. This is just a simple way. SQRTM R. Normal square root is, if you write SQRT of R, it means it will take element wise square root. But this is not okay. We are taking matrix square root, which is like this. Okay? Let me conceptually explain what this is. Let's say if I take the eigenvalue decomposition of this matrix, let's say I get some U, some D and U Hermitian. Okay, so this is D, U Hermitian, U, D, U Hermitian I get. Okay, then its square root is R 1 by 2 is equal to U, D to the power 1 by half U Hermitian. Okay. So this matrix will generate the same thing. Okay. This square root of M will do the same thing. Okay. Because you see, if you multiply R1 by 2 into R1 by 2, what will you get? U D half U Hermitian U D half U Hermitian. So U Hermitian U is identity and D half into D half is D. So you will get U D U Hermitian, which is equal to R. Okay. So if you don't want to use this, what you can do? You can take the eigenvalue decomposition and then this is a diagonal matrix. You take the square root of it. Diagonal matrix square root of diagonal matrix taking is very simple. You can use this command. Okay. It will take element wise square root. Then you just multiply back with U. You will get R half. Or you can use just same command. Both will give the same answer. Okay. Okay. So this is about the square root of a matrix. So repeat E1 to E4 for different value of correlation. Okay, so let's see this. So here I choose the value of rho to be 0.2. Then I chose R equals to, so here let's come to here. So I have to supply the first row in the MATLAB command. So it will generate the Topliss matrix accordingly. Okay. So first row is rho to the power 0 up to rho to the power n minus 1. Okay. So I generate like this, rho to the power 0 to m minus 1. Okay. So if I write here Topliss R, it will generate the Topliss matrix. Okay. Like this. Here you see value 2 and 2 are same here. Okay. The 1,2 entry and 2,1 entry. Okay. Then I take the square root of R. Okay. And I took this value. Okay. So you see RH12, I use the square root m, and here RH21, I does this procedure, second procedure, it gives me the same answer. Okay. Right. Next I choose n equal to m. So now what I am doing, correlation reduces the rates. So what I am trying to do here, for different value of correlation, I am trying to plot the rates here. Okay. So we can run this section directly. Sig2 at notch defined. We can define sig2. Sig2 equal 1. Okay. So this RH12 and RH12 underscore 1 both are similar. Then what I have done here to plot this curve. So I have taken different values of rho between 0 and 1. I have taken 10 values here, and for each value of rho I have run the loop, and for each value of rho I have generated a Topliss matrix multiplied with HW. HW is what? CN01 matrix, right? Complex quotient matrix with 0 mean and unit variance. I multiplied with square root of RH. Okay. And then I took the eigenvalue decomposition. Then I calculated the rate function, the same thing here. Then I plotted rho versus R. So you see correlation reduces the rates. As soon as we have highest correlation, the rates are approximately 0. Okay. So correlation is not desirable. Y-axis is rates. Yeah, okay. Yeah, it is not 0. It is going very low. Okay. So this, for example, we have 4x1 matrix. What can happen at most that all columns can be 1, but there still be like 1 column will remain. Okay. So minimum rank can be 1. Okay. So there can be only minimum rate. There will be some minimum rate. Okay. So let's come to exercise number 6. Okay, this part is clear, right? You can try this exercise by yourself. You have this. Go to your home, try by yourself. Okay. So answer the following question: what are the impact of number of antenna and correlation on the eigenvalues of H? Okay. Correlation reduces these values. Okay. And we have seen that if we increase the number of antenna, the value also fluctuate little bit. What are the two scenarios? Water filling doesn't have too much impact on spectral efficiency. So one is the high SNR regime. In the high SNR regime, equal power allocation is equal to water filling. Okay. The second regime is, the second scenario is based on this correlation. If we have too much correlation, this water filling will also not help. even if you allocate more power. Okay. So in which scenario water filling is needed? In the low SNR scenario. Okay. What are the criteria to achieve spatial multiplexing? No correlation. If you want to achieve highest spatial multiplexing gain is what? The slope of rate versus SNR at high SNR. Okay. If you plot rate versus SNR curve and see the slope at high SNR, that will be your multiplexing gain. Okay. You will achieve the highest rate or highest multiplexing gain when your channel is uncorrelated. If your channel has correlation, it will reduce the rates. Okay. Any question up to this point? Huh? Take a break.
So which scattering is needed
Yeah.
to get a high capacity?
Yes, yes. So how can we get uncorrelated signal? It is by rich scattering. Okay. When you have rich scattering means what? The signal is coming from multiple paths. So if you have more number of paths, you will have uncorrelated signal. Okay. Because as you see in the massive MIMO, it's like a channel hardening. I mean like law of large number, central limit theorem. That's what I want to say. So when we have large numbers, the things become uncorrelated. Okay. So in the massive MIMO, you see we have very large number, then the interference goes low. Similarly, when you have rich scattering, many number of paths are coming, law of large number, it makes the channel uncorrelated. Okay. So it means the number of paths are much higher than the number of antennas. Rich scattering means that. Okay. Should we take a break or go to this second section? Okay, 5 minutes of break. Okay. Half an hour break.
It's only 3 6. At 3:30 we will take.
3:50 we take break.
Oh.
I mean, we can move faster, but you won't get it if you don't take a break, you know.
Okay, I take a break.
We cannot go more than 1 hour.
I'm not going faster, right? Okay. Bit faster?
They should do the MATLAB program. They should have taken the computer. No, it's not just watching. It's not going to help.
If you have computer, I can send the code and you can also do the code along. Yeah, you have computers? You can also do on your mobile also if you have MATLAB app. You have laptop? Yeah, open it and I will send to madam and madam will send to you. So I have shared. When she comes, we can ask to send it to you so you can see the programs. Okay. So there are 3 programs mainly: 1.1.mlx, 2.1.mlx, 3.1.mlx. So these programs are for section 1, section 2, and section 3. Okay, correspondingly. Yeah. Can we connect the battery here? Little bit. 35%. So in the VAC is already a function in the CVX for vectorization, and MATLAB has built another function with the same name, vertical eye closer. So it is causing problem with CVX. So older version of MATLAB will work. So this massive MIMO, you search it. It will not take just talk to find a problem. You have to search it, you have to read the paper, then you have to find the problem. Yeah.
Less scattering.
Less scattering. Correlation. Uh, so one is professor said low scattering. Low scattering. It means if you, let's say you have a more number of antennas and number of paths are less, so you will get less ranked channel. Okay, if you, because the channel is usually defined by using this function. So H is equal to summation of, let's say I equals to 1 to L, some beta factor, beta I, and this is the steering vector. Okay. So channel is defined like this: the sum of all paths, if we have rich scattering, by law of large number, this becomes a CN01 value. Okay. But if we have less scattering, so let's say this is M cross 1, okay, M cross 1 vector, and M is larger than L. Okay. So what will happen is that this will have low rank. Okay. So this is a vector channel. If we make in a matrix channel, so this will have a very low rank. Okay. Yes. So L should be much larger than the number of antenna. Then we have rich scattering, and it will cause no correlation. Okay. And second thing is, if you have antennas very close to each other, it also causes correlation. Okay. Yes. So this is also one of the problem in the tutorial questions also. If you see second tutorial sheet in the, I think in the second last question, it's related to the same thing. Correlation between antennas, how much they are far, so that the correlation can be reduced. Okay. Okay. So, any other question? If you don't have question, read the second section. Yeah, you can apply. Yeah,
It's only two antennas space time.
20 now.
Space time not for. Ramon scheme only go to the.
Yeah, so at the user you need at least 2 antenna, or if you are doing the downlink, you can apply. Downlink we can apply, right? We have,
Maximum.
yeah. But it will be costly.
Yeah, you don't need a space time block for maximum.
Yeah, you don't need the space-time block code. Because of channel hardening, channel goes away. You see this channel become deterministic. Yeah. You, if you have less number of antenna, you can apply. I mean, if you want to apply, you can apply, but it will be have no meaning. That's what we want to say.
Tea is coming or
What's it?
is the tea coming or?
No, sir, tea did not come in. Yeah, you have shared just now, sir? Just now. Okay. Thanks.
We have spoken about scattering.
Hmm.
I think in this incident of wireless environment we have reflection, refraction and
Hmm.
diffraction,
Hmm.
but also on the multipath button.
Hmm.
So that will again have an impact regarding the uncorrelation what we have to. I mean, I think so.
Yeah.
That will help. That will make the scattering.
Hmm.
We want lot of scattering, lot of reflection, then we will get uncorrelated. Yes, sir. Yeah. So not only scattering, so reflection also. Everything will help. Add up, they add up and help in uncorrelated. If it is a direct line path, is the one close correlation. Okay.
The ultimately matters what are the signals we are receiving. If we are receiving multiple signals, many signals, that's are good. If some signal scatters and goes that way, it doesn't come to the receiver. I mean, we only care about the signal that is coming. Okay? Yeah.
Sir,
Yes.
I mean, I'm not used to the Dropbox. I mean, should I add to the Dropbox?
You have Dropbox?
I mean, it is this one, no?
Yeah.
How to download it?
Yeah, more options.
Activity. Add from Google Drive.
No.
Can't you send it
Yeah.
to my mail ID, sir?
1 second.
Here we have Google Drive.
Or you can directly send them the link.
You can do it.
Yeah.
I mean, here. I mean, how to do that, sir? I mean,
I will send you.
yeah, please send it to my mail ID, sir. I will just forward them. Is it many files?
You have to zip it then.
I have not logged in here. That's why it's like this. Okay, 1
I
second.
mean, don't log in, sir. I mean, they will have your password.
Okay. Copy link.
Yeah, at least remove the connection and log in.
So it will have a link also with it. If you click the link, so link is also there. Copy the whole link. Yes.
That link you should share to any person.
Yeah.
It will come, na?
Hopefully. Okay, let's check first. Check
Yeah,
first.
okay.
Oh. Yeah, it's available.
Wait, sir.
If we open incognito, copy the link. Yeah, they can download it, each file. Download button is here. Okay?
Okay. I mean, they'll be able to open, na?
Yeah. This download button is here. And you do not need to log in.
Yeah, if they open that link, they'll be able to get everything.
Yeah.
Yeah, then I will share that link.
Somebody is sleeping very heavily.
Yeah.
Yeah, participants, I forgot to mention to you. Yeah, unless you do the test now, you won't be getting that award of. Yeah, you are asking me to give both participation certificate and award of grades also, right? Yeah, that award of grade certificate, participation certificate anyway you will get, but award of grade certificate you will get only if you write the test now. Okay, na? Yeah, how many marks you are getting, that doesn't matter. No, not optional. If you want that certificate, you have to do the test now. Yeah, whether it is C grade or B grade, I mean, I can't tell. Okay.
So what time the exam start?
Whenever the sir session is over, sir. After tea break, maybe. I mean, they may skip now later, that's why I'm informing you.
Is the tea is here or not?
Tea కోసం phone చేయరా? They're calling, sir.
Have you got the link? You can download it.
Yeah, I did not send it, sir. 1 minute.
Okay. Hybrid, hybrid pre-coding. I think MIMO is here. Here impact of channel hardening is here. MRT and ZF performance are close when we increase the value of n. So n is, we are increasing, it will
సిగ్నల్ లేదు. గూగుల్ any others, can you please check? Sari is not getting the same.
Exercise. In this exercise, I am reading, let P is in minus 5 to 5 dB, N equal to K equal to 4. It means number of antenna at base station are 4, number of users are 4. Compare the total sum rate by MRT, that is FMRT is equal to H Hermitian, 0 forcing. It means FZF is equal to this expression, H Hermitian, HH Hermitian inverse, and single user MIMO with water filling. Single user MIMO with water filling we have seen earlier in here allocated power according to water filling. Okay, these three results we have to compare. Okay, where it is, yes, and then what we have to do, we have to increase the value of N and see what happens. So here we are increasing the value of N and K both, so the rate should increase, and here we are increasing, keeping the value of K constant and increasing the value of N. So it means MRT and ZF should come closer, the rates of them. Okay. Now let's see in simulation why this is not opening.
You want some help, sir?
This is not opening. I think maybe its battery is less, that's why.
Battery.
Maybe. This is not. It is not charging.
This MATLAB file, huh?
Yeah.
MATLAB file means. No. Oh. It's coming in some other language.
Yeah, it's open now.
Okay, huh?
So here, first I have written CLC clear RNG1, then initialize the transmit power values between minus 5 to 5 dB. I have taken 10 values, N dB is equal to 10, N equals to 4, K equals to 4, then I generated the channel H according to here. So this is the H, okay. Here, K comma N, then we have this sum rate R, okay. So for each value of the transmit power, I am running the loop here. So for MRT, I have chosen F equals to H Hermitian as said here, and then what I did here, I normalized it. So this normalization is the same as this. So I am dividing by this factor. Okay. So this is divided by square root of this. So I am dividing here the square root of trace of F Hermitian F. Okay. So in trace, F Hermitian F is equal to FF Hermitian. Okay. Both can be exchanged. Okay. Then I calculate the multi-user rate when I provide this H, F, and this P. Okay. So how do I calculate the multi-user rate? So this is a function I have made. So if I press here, it should open. It should be in the folder. This computer has become slow little bit. So this is the multi-user rate function. So now it will open. Yes. So I have taken the first dimension of h, that is k, using the size. Second dimension I do not care, so I have written here tilde. Then I have calculated this product hf into square root of p sigma square, that is the noise power, equal to 1, and I calculate the rate for each user separately. So the rate is given by real log 2 1 plus numerator divided by denominator. Okay. So numerator is what? Desired signal power. So desired signal power is given by h transpose fk. Okay. So that is hf k comma kth element. Okay. So I have done all the multiplication here. So I am just choosing the element here and taking the square here. So this absolute square is here. Okay. And dd is the denominator. In denominator we have interference plus noise. So this is sum of all interferences. So this summation of all interferences plus noise. Okay. Okay. So one thing, yes, sum of all interferences plus noise. Okay. So this way we can calculate the rate. Now let's come back to our program. So this is for MRT. We put f and normalize it and calculate the rate. So if there are multiple users, so this r will be a vector. As you have seen here, r equals to 0 is 1 comma k. So it will be a 1 cross k vector. And here we are taking sum for sum rate. Okay. And for the zero forcing, I just change the value of f to be like this, and the rest of it is same. And I collect the sum in this r sum 2 comma idb. Okay. This is for single user water filling. So water filling function is not working due to CVX and MATLAB issue. Okay. MATLAB already has back function, that's why. Okay. So here what I did, I defined the rate function. This is similar to the previous case, nothing different here. So I calculate the rate here, assuming we have a single user which have k antenna at the receiver and antenna at the transmitter. What will be the rate? Okay. Here. Okay. So we get something like this. So this is not running. So let's comment this for the moment and run the program. Okay. Multi-user rate. So we have here J naught equals to k, that is missing here. So let's change it. I can write here 1 to k minus 1 comma k plus 1 to k. Okay. So it means I am excluding the kth, and all of rest of them will be here. Okay. So now let's run here. It is running. It is taking too long time. I think because of this battery, this has become slow little bit in the power saving mode.
Should I give battery, sir?
We should run. Yeah, so it's here. So these are the two results for one is for MRT and one is for zero forcing. So zero forcing should give better result, but it's coming the opposite. Huh? What? Yeah. So first is MRT, second is this. One is 1 2k minus 1. It is all right. Okay. So ideally this zero forcing should come higher. I don't know why this is happening. Let's I don't know, something is not right. Okay, we'll continue tomorrow, okay? So I will bring my laptop. So water filling function, we will also show it, okay? So my laptop has older version of MATLAB installed. So this WAC function is giving the error in water filling. So MATLAB also has introduced WAC function, that is also CVX function. So both are conflicting.
I think you are having another version that laptop is having another version.
MATLAB?
Yeah, that's right.
Okay, we can try tomorrow.
Some functions are not supported in this cycle.
Yeah.
You want to go back, sir?
Yeah. There's only one MATLAB here.